Going to be working here on the homework for 8.1. It's the section on sequences. And this is off of page 434. So let me start with number 5. I want us to find a formula for the following. So we have negative 3, 2, negative 4/3, 8/9, negative 16 over 27, ... All right. Well, the first thing I'm going to notice is that we do have an alternating sequence. We have starting with a negative, then positive, negative, positive, negative. So in order to make that happen, I'm going to use what we did in class, negative 1 raised to the n. So if I replace n with 1, I'm going to get negative 1 to the 1 power, which will give me negative 1. So that times something else will make sure that we get a negative. And then when n is 2, we'll get squared, which will turn this into a positive, then negative, then positive, and negative. So that should get us the alternating sequence that we need. And then I'm going to focus on the numbers. And the first two numbers are kind of tough to see what's going on here. So I'm going to look at these fractions instead. And I'm going to try and come up with a way of generating the numbers on top and then a way of generating the numbers on the bottom. So it looks to me that this right here, this 4/3 can be written as 2 squared over 3 to the first power. This looks like 8 is 2 cubed and 9 is 3 squared. And then 16, notice I'm not worrying about the negative because I already took care of that. This next one, it looks like I've got 2 to the 4th over 3 cubed. So that looks like the pattern. Let's see if it works if I go backwards. If I go here, I would have to have 2 to the 1st because it looks like these powers are increasing by 1. So if I go backwards, it's got to come down by 1. And that means this will have to be 3 to the 0. Let's just double check this. 2 to the first power is 2. 3 to the 0 is 1. 2 over 1 is 2. So that does work. And if I follow this pattern, it's got to be 2 to the 0 over 3 to the negative 1, again, coming down by 1. Let's check what this is. 2 to the 0 is 1. 3 to the negative 1 is 1/3. And if I do 1 divided by 1/3 and flip it, I get 3. And of course, the negative was already taken care of. So that looks like it. So my first term of my sequence, or the first number in my sequence, must be 2 to the 0. So when I plug in 1, I need to get a 0 up here. Then when I plug in 2, I need to get a 1. And then when I plug in 3, I need to get a 2. So notice that the powers here, 0, 1, 2, 3, 4, those are just your counting numbers. And we need to start it at 0. So the top is going to be 2 to the n. That would be the counting numbers. Plug in 1, then 2, then 3, then 4, but I need to start at 0, so I subtract 1 from that. And that way when I plug in 1, I get 0, then I plug in 2, I get 1, and so on and so forth. Now on the bottom, it's even worse. These are the counting numbers, right? 1, 2, 3, 4, 5, but I need to start at negative 1, so I need to shift it over by 2 to the left. So it'll be 3 to the n minus 2. So if I plug in 1, I get 1 minus 2 is negative 1. That'll give me this one. When I plug in 2, I'm going to get 2 minus 2 is 0, and that gives me this one. And then it will continue. So this right here appears to be the formula, and we can just box that up and be done. Now the book might go a little further, so I'll show you what the book does on this probably. We could rewrite this as negative 1 to the n times 2 to the n times 2 to the negative 1 over 3 to the n times 3 to the negative 2. So I'm using properties of exponents that if we have the same base, different exponents, we add the exponents together. N plus negative 2 is n minus 2. So To put these two together, you would get this. We're going backwards. We're taking that, we're ripping it apart into its different factors. And the reason why we do this is because we can simplify this. This is just 1 over 2. And we can simplify this, which is 1 over 3 squared. And cleaning that up a little bit more, we get -1 to the n times I have 2 to the n. I have, let's see, what's this right here? It's 1/2 over 1/9. And then flip this up, that's 9 halves. So 9 halves. And over, sorry, I forgot to put this, over 3 to the n. And I'm going to go and do a little bit more. Since I have a 9 halves, that's a nice constant. So a sub n equals this. A sub n equals, I'm going to bring the 9 halves out to the front. And then notice that the -1, the 2, and the 3 are all raised to the n power. So what I could do is I could put these two together, like this. I could go -1 times 2, all of that to the n. And then over this right here, 3 to the n. And since this and this are both to the n, I could go -1 times 2 over 3, all of that to the n power. And if I put this together, this is just -2/3. So I have times -2/3 to the n. And that's it. That's probably what the back of the book has. Now, we can check it. Let's just, for this first one, I'll check it. A sub 1 equals, let's see, if we plug in 1 here, we get 9 halves times -2/3 to the first power is -2/3. These 2's cancel, and we get 9 divided by 3, which is 3, but then there is a negative there, so we get -3. Go a sub 2, then we get 9 halves times -2/3 squared. That's 9 halves times, let's see, if I square this, I square the top, I'm going to get 4, square the bottom, I get 9. These cancel, I get 4 over 2, which is 2. And I can keep going. Let's see, let me do a sub 3. Would be 9 halves times -2/3 cubed, which is 9 halves times, now when you cube a negative number, it stays negative, so I'm just going to throw the negative out here. 2 times 2 times 2 is 8. 3 times 3 times 3 is 27. And then we can clean this up. We have a negative, let's see, 9, 3, 1, 4. So we get 4/3. And I could keep doing this, but that matches up with the first 3 numbers that we had. And so that looks like we generated our sequence. All right. Let's look at number 6. So for number 6, we have the sequence 1, -1/3, 1/9, -1/27, 1 over 81, ... So I'm looking at these fractions, I'm getting an alternating sequence again, and it's a little different. This time I need to start with a positive, then go negative, then positive, then negative. So the way we do that is we take our -1 to the n, but we need to add 1 to that. If we add 1, then when we plug 1 in for n, we get 2, and that'll give us a squared. -1 squared is +1. Then when I plug in 2, I'll get a 3 up here, and that'll give me a -1. So that'll create the alternating we need. And then I'm going to look at the fraction. Looks like the entire time the numerator is 1. And then the bottom, these look like powers of 3. 3 to the 1, 3 squared, 3 cubed, 3 to the 4th. And that would mean this needs to be 3 to the 0. And on the bottom, you can't really see it here, but rewrite it as 1 over 1. And so you can match this up. 3 to the 0 is the bottom. Well, 3 to 0 is 1, so that does work. So what I need on the bottom is 3, and then I need to start at 0 and just count numbers. So n minus 1. All right, that would be good enough for me. You box that up, but let's try and take this a little further. This is negative 1 to the n times negative 1. So what I'm doing is I'm trying to get everything written out so I get powers of n on things so I can put them together. So what I do is I use the fact that this addition up here turns into this, right, because there's really a 1 there. And then you would add those two exponents together. Then I have times 1 over, and on the bottom, n, 3 to the n times 3 to the negative 1. And keep going here. All right, so the things that I have to the n are this, which is on the bottom, and then this, which is on the top. So I can rewrite that as negative 1 over 3 to the n. And then I have a negative 1 here over this. Now, on the bottom, this really means 1/3. And since it's on the bottom, I flip it up as a 3. So I should have written this. Negative 1, that's this one. And then the 3 comes up. The 3 comes up. So that comes up. And one last thing. I'll put these two together and put them out front. So negative 3 times negative 1/3 to the n. Shall we check? If n is 1, you get negative 3 times negative 1/3, which is positive 1, which was our first guy here. If I go n is 2, let me see, n is 2, we get negative 3 times negative 1/3 squared, which is negative 3 times 1/9. So when you square that, you get 1/9. And then the negative times a positive is negative. That's good. The 3 and the 9 reduce out, and you get the 1/3. So this works. Let's look at 7. One half, negative 4/3, 9/4, negative 16/5, 25/6, ... Okay, we have an alternating sequence again. So let me take care of that first. Need to start it with positives, so I'm going to put n plus 1. And then let's take a look at the fractions. Well, the bottom is just counting numbers, 2, 3, 4, 5, 6, starting with 2. So to do that, I put n plus 1. That way when I write this counts by ones, 1, 2, 3, 4, 5, but I need to start at 2, so I add 1. So if n is 1, I get 2. If n is 2, I get 3. If n is 3, I get 4, and that'll create the bottoms. The tops, on the other hand, what do those look like? Well, you could say that this is 2 squared, but then this is not 2 to the 3rd power. So these aren't powers of 2 up here, but they all look like perfect squares. Like 4 is 2 squared, 9 is 3 squared, 16 is 4 squared, 25 is 5 squared, and that means this first one would have to be 1 squared. So it looks like it's always a squared, so I always have a squared, but the base is actually just the counting numbers, 1, 2, 3, 4, 5. So if I put n here, n squared, that should do it. And in this problem, I'm not going to clean this up at all because I can't simplify like I did earlier, because in the earlier 2 problems, our exponents over here had n's in the powers. Here, there's no n's in the powers, so I'm just going to leave this expression just like this. I won't check it, but you can verify for yourself that that does work. Okay, what are we on? Number 8. Five, 8, 11, 14, 17, ... So what's going on here? Notice that each of these, it's just going up by 3 each time. Just keeps on going up by 3. So this first one is like 5. This one's like 5 plus 3. This one is like 5 plus 3 plus 3. This one's like 5 plus 3 plus 3 plus 3. This next one is 5 plus 3 plus 3 plus 3 plus 3. So each time I take a step into the next number, I keep adding another 3. And remember that addition, right? Repeated addition can be rewritten as multiplication. So this right here is the same as 3 times 2. This is the same as 3 times 3. This is the same as 3 times 4. And this first one right here would be the same as 3 times 1. So it looks like what I can do is I can take the number 5. So let me try and write my formula out. Take the number 5 and then add to it multiples of 3. I know that when I'm in my second number, I need to add 1 multiple of 3. When I'm at my third number, I need to add 2 multiples of 3. When I'm in my fourth number, I need to add 3 multiples of 3. When I'm at my fifth number, I need to add 4 multiples of 3. So it looks like if I put n here, it's not quite going to work. If I do n, because look, if I plug in 1, right, I'm going to get 8 and I need to get 5. If I plug in 2, I'm going to get 6 plus 5, that's 11. So I'm off. This is actually shifted over too far. I'm starting here instead of here. So what I need to do is when I plug in 1, I need to just get 5. And when I plug in 2, I need to get a 1 here. When I plug in 3, I need to get a 2 here. So what I'm going to do is I'm going to shift this n minus 1 like that. And now when I plug in 1, I get 0 here. This all goes away. I get 5 here. When I plug in 2, I get a 1 here. That gives me a 3 times 1 is 3. 3 times 1 is 3. Add 5, we get 8. And then I keep going. And that's it. That'll work. I'm going to clean up. I'm going to distribute through. So 5 plus 3n minus 3. So we get 3n plus 2. Now, that's another thing, now that we see how clean this formula is, that's another thing we could have noticed from the very beginning. Let me show you. If I start this problem over in retrospect, if I write down all the multiples of 3, we get 3, 6, 9, 12, right, 15. Those are the multiples of 3, and I could create that using 3n. Each of these is just the multiple of 3 plus 2, right? Take 3, add 2, take 6, add 2, take 9, add 2. So if I just add 2 to each of these numbers, I should create this list. And like I said, going back and looking at it now and seeing this formula, this might have been easier to do, but would you have seen that right away? Probably not. You'd probably have seen that they keep going up. They keep going up by 3 on each step. So that's why I showed it to you that other way initially. All right, number 9. All right, for these, we want to figure out if these sequences converge or diverge. And if they converge, we're supposed to find out what they converge to. So in this, when they say converge, what I'm doing is I'm taking the limit as n goes to infinity of a sub n. So for this problem, it's the limit as n goes to infinity of 1 minus 0.2 to the n. And now just let n go to infinity. So what happens to this as we start raising it to bigger and bigger powers? So to help you see this in case you're having trouble seeing it, 0.2 is the same as 2/10, right? That's what 0.2 is, raised to the n power. So what happens if I plug in 1? If I plug in 1, get 2/10 to the first power, which is 2/10. If I plug in 2, so I'm letting n get bigger, this becomes 4/100ths, which actually got smaller than when I plug in 1. If I plug in 3, I get 8/1000, and that's even smaller than this. So what's happening is as n gets bigger, this number right here raised to the n gets smaller. So what's happening is this is approaching 0. And so we have 1 minus 0, which is headed towards 1. So as n gets bigger, this thing, this expression, this sequence should get smaller and smaller. This one right here should get smaller, and so we should get something closer and closer and closer to 1. Remember, we're not saying we'll ever get to 1. We're just saying that's what we're approaching. So the answer is 1. It converges. So the answer would be it converges. And then what does it converge to? What's the limit? It's 1. Okay, 10. A sub n equals n cubed over n cubed plus 1. All right, so what happens here if we take the limit as n goes to infinity of n cubed over n cubed plus 1? Well, the top is getting bigger and bigger and bigger, right? The top is headed to infinity, and the bottom is also headed to infinity. And whenever we had that back in Cal 1, we used something called L'Hopital's rule. You can go look that up on my videos for Cal 1 if you need to, a review of L'Hopital's rule. But the problem that we have is that to do L'Hopital's rule, and I discussed this in my lecture, but I'll say it again. To use L'Hopital's rule, we rely on the derivative of the function. And we know that sequences are not functions. When we graph a sequence, it's dots. And so you can't talk about derivatives because derivative is a slope of a tangent line. And so we actually need a curve before we can talk about the slope of a tangent line. You can't talk about the slope of a tangent line at a single point if there's nothing else next to it, right? The next point's far away from it. So you can't get arbitrarily close and get that slope. So the derivative completely goes away, and so we can't use L'Hopital's rule. But there was a theorem that said if we do look at this limit and we replace our n's with x's, so we take the limit as x goes to infinity of x cubed over x cubed plus 1, where we're treating x as if it's a real number. What that means is we are looking at the graph of this thing as a function which draws a curve, realizing that our sequence, if we just do the ends, like plug in 1 we get this, and plug in 2 we get this, whatever the function does, the black curve, the sequence must also do. So it's a subtle thing here, but we have to convert the sequence into a function where we're allowing the variable to be in the real numbers instead of just the integers or just the natural numbers. Then we can apply L'Hopital's rule. So L'Hopital's rule says that if you have infinity over infinity, you can redo the limit and just take the derivative of the top over the derivative of the bottom, which in this case is the exact same thing. And then that just simplifies to be 1. And that's the answer. So whatever this does, according to the theorem I said in class, whatever this one does, this does the same thing. So the answer up here is 1. What you want to be careful to not do is you don't want to just rewrite this with just leaving your ends, because you can't use L'Hopital's rule on a sequence, if that makes sense. Hopefully it does by now. So, all right, let's look at number 10. Number 11, sorry. A sub n or I'm going to write the limit now because that's what I'm going to be trying to do. Save myself some time. Limit n goes to infinity of 3 plus phi n squared over n plus n squared. All right, this is going to go in, we're going to do this the exact same way. If we let n go to infinity, we get infinity over infinity. That's where this is headed. So I'm going to rewrite it, replacing all of the n's with x's, and treating this as a function of x, where x is in the real numbers. And then I can apply L'Hopital's rule. Derivative of the top, 10x. Derivative of the bottom, 1 plus 2x. And this still goes to infinity over infinity. And so I apply L'Hopital's rule again. Derivative of the top is 10. Derivative of the bottom is 2. We get 5. So the answer to the original question is that it converges to 5. And keep in mind what we're saying. We're saying that with this original sequence, right here, if you were to list out the numbers, like if I plug in 1, let's see what I get. I get 8 on top, plug in 1 here, I get 2, that's a 4. And then if I plug in 2, I get another number, another number. What I can tell you is that the further out in this list I go, the closer and closer I get to 5. Without actually ever necessarily getting there, I can tell you that these numbers get closer and closer to 5 the further out I go. Right? I'm just trying to keep everything in perspective, like what it is we're saying here. Trying to determine where the sequence goes to. Okay, I think 12, well, we'll do 12. A sub n equals n cubed over n plus 1. Same thing, I get infinity over infinity when I, oh, well, I don't have my limit in there. I should have written my limit. Let me do that. That's the original sequence. I got to remember to start writing limits on these. Limit n goes to infinity. This goes to infinity over infinity. So I rewrite it where x is a real number, x cubed over x plus 1. I'm going to apply L'Hopital's rule. Derivative of the top is 3x squared. Derivative of the bottom is 1. And now we get something a little different than what we've seen before. As x gets bigger, the top gets bigger, the bottom is just 1. So this is headed to infinity. And there's nothing else you can say about that. It's getting huge. So what we say is that this diverges. It's got to head to a specific number for us to say it converges. All right, 13. All right. So limit n goes to infinity of tangent of 2n pi over 1 plus 8n. Wow, okay, that looks different. So if n goes to infinity, the top here goes to infinity, and the bottom here goes to infinity. So inside here we're getting infinity over infinity. Well, we've done L'Hopital's rule in the past when we had that. So let me try this here. First of all, I'm going to rewrite this with x's, where x is a real number. And I'm just going to look at the inside. I'll come back and deal with tangent in a second. 2x pi over 1 plus 8x. If I do L'Hopital's rule on this, derivative of the top is 2 pi. Derivative of the bottom is 8. And that's just pi over 4. So what I'm saying is that as the x gets bigger and bigger and bigger, this thing heads towards pi over 4. That's what the inside of this is headed to, right? Because whatever this does over x, that's what happens over n also. So I know that the inside of this is going to pi over 4, which means that this is headed to tangent of pi over 4, which is just 1. So this sequence converges to 1. Do 14, then take a little break. Just a quick one. So limit n goes to infinity of 3 to the n plus 2 over 5 to the n. So as n gets huge, this gets big. 3 to a big number becomes huge. So this is going to head towards infinity over, and then 5 to a huge number becomes huge. This is infinity over infinity. So you're thinking L'Hopital's rule because that's what we've been doing. We actually don't need it here, and I'll show you why. Because both the 3 and the 5 are raised to the n power, I can rewrite the top like this. We did this earlier when we were trying to find the formulas. That's equal to limit n goes to infinity of 3 over 5 to the n times 9. So I put these two together into a single fraction. 3 squared is 9. And so I'm trying to figure out what happens here. Well, we saw this earlier when we did this, 0.2 to the n. We know that if the number in here is smaller than 1, then as you raise it to powers, it actually gets smaller, right? If I just look at 3/5 to the first power is 3/5. 3/5 squared is 9/25. And if you compare these two, this one is smaller than this one. And then as I keep going, it gets smaller and smaller and smaller. So as long as the number in here is less than 1, it's going to get smaller. And so this piece right here heads to 0. And then times 9, that doesn't really matter. The whole thing is converging to 0. So I did not need L'Hopital's rule for that. All right, quick break. Fifteen. Limit n goes to infinity, n squared over square root n cubed plus n. All right, so if we take a quick look at this, we'll realize that we get infinity over infinity again, right? As the top gets bigger, the bottom gets bigger. So you might be wanting to do L'Hopital's rule again. However, the derivative of this bottom piece is going to be pretty ugly, and I'm not quite sure I want to deal with that. So I'm going to use a different technique that we've used in Cal 1, and that's how can we turn this highest power of the denominator, which is n cubed, how can I turn that into a 1? Well, I can always turn n cubed into 1 if I divide by n cubed. So what I'm going to do is I'm going to be very clever here, and I'm going to introduce a 1 over n cubed right here. But I have to do it on the outside, so watch what I do. I'm going to do a square root of 1 over n cubed. And whatever I do at the bottom, I have to do the top. Like that. So this is a 1. And what happens here is since you have two roots that are multiplying together, I'm going to do the bottom first. These two roots become a single root, and then it's this times these two. So I'm going to distribute that through, but I'll do it on the next step. 1 over n cubed plus n, like that. Now on the top, this is a little more complicated, all right, because this kind of looks ugly. So what I'll do is I'll rewrite this as 1 over n cubed to the 1/2. That's what this is. And then I'll raise 1 to the 1/2, which is 1. And I'll raise n cubed to the 1/2. So I get 1 over n to the 3/2. So that's what the top is, multiplying those two together. And so I'm taking 1 over n to the 3/2 times n squared, which is the same as n squared over n to the 3/2. And then I subtract powers. 2 take away 3/2 is going to be 1/2. So the top is just n to the 1/2. Now on the bottom, what happens we have n to the 1/2 up top. On the bottom, when I distribute through here and here, I get 1, and then I get 1 over n squared. And so as n gets huge now, let's see what happens. N goes to infinity, the top goes to infinity, and the bottom, this right here, goes to 0. Fixed number over a huge number that gets really small. So I get 1 plus, oh, I forgot the square root. I get 0 here, I get 1 plus 0, which is 1. Square root of 1 is 1. So the bottom is headed to 1. We no longer have infinity over infinity. What we have instead is infinity over 1. And that heads to infinity. And so this diverges. So no L'Hopital's rule, just a clever usage of a multiplication by 1. And that's kind of a standard technique, so please be aware of it. 16. Limit n goes to infinity, square root n plus 1 over 9n plus 1. Now, when we take n and let n get big here, this top goes to infinity, the bottom goes to infinity, and then square root. So we have infinity over infinity. And whenever we've had that in the past, we've actually seen a couple of different things we can do. But L'Hopital seems good here because the derivative of this and this by themselves are pretty simple. Now, because we are going to use L'Hopital's rule extensively, and because we get tired of writing, switching this to x, I'm just going to write this down. This equals, by L'Hopital's rule, limit as n goes to infinity of, let's see, well, you know what? Let me be precise. I don't want to take any shortcuts here. Let me do this. I want to know what's happening to this, right? I know it's infinity over infinity. I'm going to switch everything to x first. X is a real number. And let me just look at this inside piece. X plus 1 over 9x plus 1. By L'Hopital's rule, this is going to go to 1 over 9. So that's going to 1/9. So I know that this is headed to the square root of 1/9, which is going to be 1/3. Just take the square root of the top and bottom. So it converges to 1/3. Okay, next one, 17. Limit n goes to infinity of -1 to the n over 2 root n. Now this is the first time we've had an alternating sequence, and we're trying to figure out what happens as n goes to infinity. The problem that we're going to run into is that the numerator is not headed to anything. It keeps flip-flopping back and forth. It's going from 1, then -1, 1, -1, 1, -1, back and forth and back and forth and back and forth. The bottom, on the other hand, is headed to infinity. So what we're going to do is we're going to use a theorem that said if the absolute value of a sequence goes to 0, then the sequence goes to 0. That's a very nice theorem. So let's use that. Let me take this. This is my a sub n. Let's look at the absolute value of it. So what is the limit as n goes to infinity of the absolute value of -1 to the n over 2 root n? Well, when you take the absolute value of a fraction, you do the top and bottom separately, the absolute value of the top will always spit out a +1. Because no matter what this changes between positive and -1, once you hit it with the absolute value, it's just 1. So that turns into, this turns into the limit as n goes to infinity of 1 over, now the absolute value of the bottom you don't need because the square root of n will always be a positive number. So this is always going to spit out a positive number on the bottom. So I'm just going to write 2 root n. And it's pretty obvious what happens here. As n gets bigger, this thing goes to 0. And so if the absolute value of the sequence goes to 0, which it does, then the original sequence goes to 0. So the answer to this one would be it converges to 0. Just be careful on this theorem. The theorem says if the absolute value goes to 0, then the original one goes to 0. If the absolute value of the original one goes to something like 1, anything other than 0, then this theorem, you throw it out the window. You can't use it. All right. 18 looks like another one of these. So for 18, you have limit n goes to infinity of -1 to the n plus 1. That's an alternating sequence over times n over n plus root n. So what's happening here? On the top, it's getting big, right? This is getting big, but it's alternating between positive and negative numbers. And the bottom is going to infinity. So we almost have like an infinity over infinity, except for the fact that the top keeps switching between positive and negative. So let me see here. Let me try that theorem. What's the limit as n goes to infinity of the absolute value of this? Well, the absolute value of this piece right here is just going to spit out 1. So we have limit n goes to infinity of 1 times n, so that's n over root n. And then if you go through and apply L'Hopital's rule, I'm not going to show the work because now we're at infinity over infinity. You do L'Hopital's rule, that will turn out to be 1. And so you get that your answer is 1 here, right? Does that mean that this converges to 1? It absolutely does not mean that. because the theorem said that it had to go to 0. If the absolute value goes to 0, then that goes to 0. But if it goes somewhere other than 0, then it doesn't work. So what we know is this. We know that this piece right here, which really is constituted by this piece, that's headed to 1. So let me try and draw a picture of what's happening in this sequence. If this is 1 and this is -1, what's happening here is that as I go out further and further, this piece right here is going to try and force this ratio to be a 1. But this is going to switch it back and forth between positive and negative. So it's getting closer to 1, then -1, then 1, then -1. So if I imagine having like a horizontal line out here, the further I go out, my sequence is getting closer to 1, but then on the next step it'll be closer to -1, and the next step closer to 1, and then next step closer to -1, and it keeps doing this. So you're getting this scattered kind of, back and forth, and so you cannot say that this sequence converges. For it to converge, it has to go to one place, and this one, it is going to a certain number, but it's just the number positive and negative, and that doesn't work. It has to be one specific number. So this scattering of our sequence tells us that this thing diverges. You might be asking yourself, well, how am I supposed to write that down as an answer, Well, you just write down pretty much what I just said. Use sentences. Explain what's going on. All right, 19. Limit n goes to infinity, cosine n over 2. So as n gets bigger, we get infinity over 2, which is becoming infinite. So what does cosine do as you go out to infinity? So we know that the cosine curve looks like this. And since this is a sequence, it's just certain points on that, right? I don't even know where those points are, but... And I hope it's pretty obvious from this that the further you go out, that these dots, these black dots, are just going to be scattered all over the place. And they're not headed to one particular number. So this one would diverge. Now, what would happen, just for curiosity's sake, what would happen if I replace this with 2 over n? Now, that's a totally different function. So as n gets bigger, the inside goes to 0, and cosine of 0 heads to 1. So it would converge to 1 if that were flipped over. Just I will show you the difference. 20. Oh, how about that? That's exactly what they did on number 20. Hilarious. I didn't even look at that. I could foresee the future. 21 then. All right, so they give you the sequence in braces. So this is just a different way of defining the sequence. It means exactly the same thing as earlier. So that's what they write, and they say, does it converge or diverge? So what I'm saying is, if you erase the braces, and you put a sub n equals this, it's just the same exact thing. So what I want to do is I want to take the limit as n goes to infinity of this. So the top is a huge number, factorial is a huge number, infinity, and then infinity again. So you're thinking maybe L'Hopital. Well, the problem with L'Hopital is that in order to use L'Hopital, we had to convert this into a function of x, where x is a real number. Factorials are only defined when these are integers. So you're not allowed to let these be x's, because you can't do factorials of things like 1/2. At least not in this class we can't. So if these have to stick to being integers, we cannot convert this over to a nice smooth function. Hope that makes sense. So we're stuck. No L'Hopital's rule. So what we're going to use here are the properties of factorials. So how about this? We notice that the denominator, the factorial denominator is bigger than the one on top because it's n plus 1, or 2n plus 1 instead of 2n minus 1. So what I'm going to do is start peeling off factors. So the first factor of this would be this. Then I reduce it by 1, 2n. Then I reduce it by 1 again, 2n minus 1. And then I keep going down and down and down. But 2n minus 1, the rest of the way this way, is actually 2n minus 1 factorial. So these two now match and they cancel. And I think I'm going to have to get out of here. Look, what's my time here? 50 minutes. This will be perfect. Okay, so what I'm left with is the limit as n goes to infinity of 1 over 2n plus 1 times 2n, and that goes to 0. Are you here for the Cal 2 study group? No. Are you doing a study group?
Yeah, no, I'm sure not yet.
What time, 10? Okay, let me know. I'm going to try and work through a few more problems. Okay. This might be the last one I can do right now. 22. So we have limit n goes to infinity of arctangent of n over n. So arctangent of n, this gets huge over this, which gets huge. So I know the bottom is headed towards infinity. Question is, what's the bottom headed towards? I mean the top. So arctangent of infinity doesn't really make a whole lot of sense. But what we do is we go back to the graph of tangent. Pi over 2, negative pi over 2. We dealt with this when we did improper integrals. We know tangent looks like this. And so when you say arctangent of infinity, you're saying where on the tangent function is the graph becoming infinite, going to positive infinity. And that's happening when you try and let the angle become pi over 2. So the top here has got to be headed towards pi over 2. And pi over 2 is a nice fixed number. And when you take a nice fixed number and divide it by a huge number, this thing goes to 0. So this converges to 0. All right, that's all I've got time for right now. All right, I'm going to see if I can knock out the rest of this 8.1 in the next 30 minutes. All right, so I stopped at number 22. I'm just going to do the odds now, although you should try and do the evens also. Number 23, the sequence is n squared e to the negative n. And we're trying to figure out if this converges or diverges. So I need to figure out the limit as n goes to infinity of, I'm going to rewrite this as n squared over e to the positive n, just using the fact that negative n drops it down. I realize that both of these go to infinity, so I get infinity over infinity. So what I will do is I will transform this first into a real valued function, and that way I can use L'Hopital's rule to take the derivative of top and bottom separately, which will give me 2x over e to the x. And that still goes to infinity over infinity, so I apply L'Hopital's rule one more time. I get 2 over e to the x, and then now the top is fixed, the bottom goes to infinity, this goes to 0. Therefore, this limit goes to 0. So that sequence converges to 0. All right, for the next one, we have a sub n is cosine squared n over 2 to the n. And so as n goes to infinity, cosine oscillates, jumps around between -1 and 1, and a bunch of things in between there too. And then when you square it, that means everything that was negative is now positive. So the top is just kind of jumping around through positive numbers, but the bottom is going to infinity. So what I'm going to use here is a squeeze theorem. I'm going to first place cosine n between -1 and 1 because I know it's definitely between -1 and 1. And then when I square it, what I can say is that this has to be less than or equal to 1, but this now has to be greater than or equal to 0 because anytime you square something, it can't be negative. And then I'm going to divide everything by 2 to the n. And therefore, I've got the sequence I'm interested in, a sub n in the middle, and I've squeezed it between two things. Now, this is just always 0. Okay, but on this one, if I take the limit as n goes to infinity of this thing also goes to 0. And so what I've done is I've squeezed the sequence I'm interested in between two things, 0 and 0. And the only number between 0 and 0 is 0 itself. So this converges to 0. All right, 27. 27 I did in class. So I'm not going to do that one. You can watch the lecture video for that. There was quite a bit involved there. And I believe 28, I did something like 28 in class also. 29, your sequence is 0, 1, 0, 0, 1, 0, 0, 0, 1, and I suppose the next one would be 0, 0, 0, 0, and then 1. So what's happening is every time I go out, I'm going to put 0, then a 1, then 2 zeros and a 1, then 3 zeros and a 1, then 4 zeros and a 1, the next one will be 5 zeros and a 1, and that's definitely, this sequence is definitely not going to any particular number. It's going to 0 for a while, then it switches to 1, then it goes to 0, then 1, 0, then 1. Give me just a second. I thought you had class. I thought you had class. Oh, really?
Yeah.
Oh, okay. Because Letty was telling me you came by. Give me just a minute here and let me finish up. I've got 2 more problems to do, if you don't mind. Okay. All right. So the next one, a sub n equals natural log 2n squared plus 1 minus natural log of n squared plus 1. So on the previous problem, the answer would be that it diverged just by inspection of the sequence. So here is if we take the limit as n goes to infinity of this sequence, notice this goes to infinity, and then natural log of infinity goes to infinity. This goes to infinity, and natural log of infinity goes to infinity. So what we have here is an infinity minus an infinity, and that is still an indeterminate form. So we got to figure out what's going on. So I'm going to use the property of logs here. Since I have a natural log of something minus another natural log of something, I can turn the 2 logs into 1 log with division. And now at this point, if I let n go to infinity, I get infinity over infinity in here. And that I can use L'Hopital's rule on. So what I'm going to do is I'm going to switch over to x, and I'm just going to look at the part inside. Just figure out where that goes. So applying L'Hopital's rule, derivative of the top is going to be 4x. Derivative of the bottom is 2x. These cancel, and you just get the number 2. So what I know is that the inside of this, as n goes to infinity, the inside of this actually goes to 2. And so our answer here is that this converges to the natural log of 2. Whatever that is, that's a number. Okay, the last one. This one's a little tricky. Oh wait, that was the last one. I was going to look at 32 though. I thought that was interesting. A sub n equals -3 to the n over n factorial. Okay, so let's try and figure out what is going on here. We know that this thing is alternating because you have a negative 3 to the n power, so it's going to be a negative, then a positive, then a negative, positive, negative, positive. And the bottom is going to infinity. So this is going to infinity, but this is also going to infinity. This one switches back and forth between positive and negative numbers. So let me try this theorem. Let me look at the absolute value of this. If I take the absolute value of this, the absolute value of negative 3 to the n over the absolute value of the factorial is still the factorial. This takes away that negative, so you just get 3 to the n over n factorial. And what I'm hoping for is I'm hoping that this thing goes to 0, because the theorem told us that if the absolute value of the sequence goes to 0, then the sequence itself must go to 0. So if this, then this. So I'm hoping this goes to 0. So let me try it. Let me see if I can convince you of this. This is not a very natural thing. So let me see here. Let me just write out what this is first. 3 to the n over n factorial is equal to 3 times 3 times 3 all the way out, and then eventually I stop. And then n factorial is n minus 1, n minus 2, all the way down until I get to 1. So let me do this for a particular n. Let's say n was 5. Then what I would get would be 3 times 3 times 3 times 3 times 3 over 5 times 4 times 3 times 2 times 1. And so what I'm going to hope for is that I can somehow get some control over this. Notice that this number, right, is bigger than 1. This number is bigger than 1. This number is bigger than, or is 1. This number is smaller than 1. This number is smaller than 1. So those three, I can just cancel them out. So here's the thing we're trying to see here. If I let n get bigger, n be 7, then we're going to have 3, 3, 3, 3, 3, 3, 3 over, and then, let's see, 1, 2, 3, 4, 5, 6, 7. We've got 7 times 6 times 5 times 4 times 3 times 2 times 1. So notice this is where we get the 3's to cancel. These two are greater than 1, right? But these are all less than 1. So what's happening here is, what I'm going to do is almost like a squeeze theorem. I'm going to try and get this thing to be smaller than something. So what we need to notice in both of these, there are only 2 numbers that will ever be bigger than 1, okay? And so as I let n get bigger, I'll still have a 3 over 1, then a 3 over 2, then a 3 over 3, except now I'm going to have more of these, and all of these are smaller than 1. So let's see if you can follow me on this logic here. Do you agree with this? Do you agree that 0 is less than or equal to 3 times 3 times 3 times 3 times ... And then I'll have 3 times 3 times 3 at the end. And then n times n minus 1 times n minus 2 times n minus 3. And then I go all the way down to 3 to 1. So we already know that at this point in time, we'll have a 1 there. We know these two are bigger than 1. In fact, this is just 3 halves, and this one is just going to be 3. The rest of these, all of these, are all less than 1. So what I'm going to do is this. I'm just going to look at these right here. Okay? If every single one of those is less than 1, less than 1, less than 1, then when I multiply them together, all of these together are less than 1. So tell me if you see, well, don't tell me because you can't tell me, what you think of this. 3 over n, which is the very front, I didn't touch it, times 1 times these two multiplied together, which would be 9 halves. Do you agree that this is bigger than this? Well, 3 over 9 is this, 3 over n is the same thing as this. 9 over 2 will always be these first ones.
And then all of these we said were less than 1. So if you multiply them together, they're less than 1. So all of that, if that's smaller than 1, then if I put a 1 here, that's bigger than all that.
And this is real nice because we can just multiply across. We get 27 over 2n.
And so this over here, this side is 0. And if we take the limit now and we let n go to infinity, this right here will go to 0. And that means the thing in the middle that we are looking at must also go to 0. So the answer is that it converges to 0. Okay, when I do the video for the homework for 8.2, I will do the last problems out of this section, which are 37, 38, 39, and 40. I didn't really get a chance to cover that in lecture, so you'll just have to wait. I'll try and get that video out tomorrow morning. I'm going to be working on the homework solutions for 8.2, but there were still a couple of problems from 8.1 that I had not completed that I said I would complete. So let me get to those first. Now, what we're kind of relying on here for these problems is this theorem that I did in class that said every bounded monotonic sequence converges. So if someone gives us a sequence, if we can show it's bounded and we can show it's monotonic, then the conclusion is that it converges. It doesn't tell us what it converges to, but it does tell us that we have convergence. So we're going to look at number 37. The sequence is 1 over 2n plus 3. Now we know that this converges. I mean, there's no question about this, because if we let n go to infinity, it's pretty obvious that we're going to get 0. What I'd like for us to do, though, is get used to the idea of how to show something as bounded and how it's monotonic. So the instructions say, determine whether it is increasing or decreasing or not monotonic at all. And then, is the sequence bounded? So although we know it converges already, I'm going to just practice showing these two things. So first of all, what do we think it's doing? As far as the monotonic is concerned, is it increasing or is it decreasing? And it could be doing neither one, but okay, that's what checking for the monotonic means. It's going to be this one or possibly neither one. So let's just look at the sequence. If I plug in 1, I get 1/5. I plug in 2, let's see, I get 1/7. Plug in 3, I get 6, 9, 1/9, and so on and so forth. So it looks like these are getting smaller as I go, which means that it appears to me that it's decreasing. So that's what I want to try and show. I want to show a sub n is decreasing. To show that it's decreasing, I need to show that a sub n is greater than a sub n plus 1. Right? That's the definition of decreasing. The nth term of the sequence, whatever dot that is on our plot of this, it's going to be higher than the one next to it. So as long as that continues to happen, we know that this sequence decreases. So I've got to show that inequality. All right? If I can show that this is true, then I'm done. So what I'm going to do is I'm going to first show, what is a sub n? Well, a sub n is just that expression, 1 over 2n plus 3. I want to show that that's bigger than a sub n plus 1. So that's this same sequence right here, but replacing that n with n plus 1. So I would get 1 over 2, replace the n with n plus 1, then plus 3. Now let me try and convince you that this is always true. So what I'll do is I'll distribute the 2 through here. 2n and then plus 2 and then plus 3 is plus 5. So I think I could probably convince you right here that it's true because this number is bigger than this number. We kind of knew that already here, but just watch as I go through this. Let me show you how I can definitively convince you that this is true. So what I'll do now is I'll kind of like cross multiply. I'm going to multiply this side times 2n plus 5. At the same time, I'm going to multiply this side by 2n plus 5. That will clear out this fraction over here. I don't have to worry about flipping the inequality over because this is guaranteed to be a positive number, right? Because n is positive. And then at the same time, I'm going to multiply both sides by 2n plus 3. 2n plus 3. And that will cancel the fraction out on the left side. So I get this and this cancel. I get this and this cancel. And so I'm left with 2n plus 5 times 1, which is 2n plus 5, is greater than, and then over here I'm just left with 2n plus 3. Now I'll just subtract 2n on both sides. They just happen to cancel, and I get the inequality 5 is greater than 3. And the question is, we were saying, is this true? If this is true, then it's decreasing. And we plug things in, and we got this as a conclusion. Well, this is always true. Always true. So I'll say true for all n. Okay? 5 is always greater than 3 no matter what. So what I've shown is that it's decreasing. Okay, now the next thing to do is to show it's bounded. So to show it's bounded, I have to show that the sequence of numbers always stays between two numbers. It's always, these numbers are always bigger than something, and they're always smaller than something. So what does it seem like is reasonable here? So for bounded, I want to show that my sequence, a sub n, is stuck between two numbers, something and something. If I can show that, then I can say it's bounded. I think the obvious choice for what it's greater than is 0, right? Because all these are positive numbers. And let me put in this right here. That's our sequence. But what is that always smaller than? Well, I think that all of these are going to be fractions, right? One's always going to be on top. They're going to get smaller. So 1 would be a natural choice. So let's just check to see that this is true. First of all, checking that one. If we multiply both sides by 2n plus 3, right? So I'm doing two separate problems here. I'm trying to show this is true first. Multiply both sides by 2n plus 3. It goes away here, and 0 times 2n plus 3 is 0. So I get 0 is less than 1. That checks, okay? That's always true. Now what I want to show is that 1 over 2n plus 3 is less than 1. So I'll multiply both sides by 2n plus 3. I'll get 1 is less than 2n plus 3. And now what I'll do is I will subtract 3 from both sides and get negative 2 less than 2n. And I'll divide both sides by 2 to get negative 1 is less than n. So this will be true as long as n is bigger than negative 1. But remember, n always starts at 1, then 2, then 3. So this is going to check also because it's a sequence and we start at n equals 1. So this is good to go. So what we've shown is that this sequence is bounded, right? So we've shown it's monotonic, we've shown it's bounded, and therefore it must converge, even though we already knew that to begin with. Okay, but that's how you do it. So what's most important here is the actual technique, the method, because the problems get a little more challenging. So let's look at the next one. So for 38, we have 2n minus 3 over 3n plus 4. And let's work on the monotonic part first, all right? So let's try and take a guess as to what we think is happening here. And to do that, we might have to write out some of these. So if n is 1, let's see what I get. n is 1, I get negative 1 on top. And then if n is 1 on the bottom, I get 7. And then if I do n is 2 on top, I get 1. On the bottom, 2, 60, we get 10. And then the next one, if n is 3, 6 minus 3 is 3. On the bottom, we get 13. So if we continue this pattern, it's going to be 5 over 16, then 7 over 19. 19. So if we look at this, can we tell what's happening with this sequence? Is it getting bigger or smaller? Well, it looks like we're starting out, if we were to graph this, if we plug in 1, we're at negative 1/7. We plug in 2, we're at 1/10. We plug in 3, we're at 3 over 13, which is actually bigger than 1/10. Or is it 3/13, 1/10? How do you compare these to see, without a calculator, how do you compare 1/10 and 3/13? Well, you get a common denominator. So 130, so I multiply 13 on top and bottom here. And then here I multiply top and bottom by 10. And so with the common denominator, these two rewritten, you can tell that 130 is bigger than 13 130ths. So yes, this number, 3/13 is bigger than 1/10. And then let me check 5/16. If I were to compare 3/13 to 5/16, then what we could do, we got a common denominator here, a faster way of doing it, okay, to check which side is bigger, is to multiply this times this. So 16 times 3, that's 30, that's 48. And then you do this times this, and that's 50, 65. And since this times this side is a bigger number than this side, this fraction is bigger. So I know that this is bigger than this, so it's a little bit above. And this keeps happening, okay? That's what it looks like is going on. So it looks like my sequence is increasing. So that's what I'm going to try and show. So I want to show that a sub n is increasing, getting bigger as I go. All right, well, then what I need to show is that a sub n is less than a sub n plus 1. This is opposite of what we showed last time. So I want to show this. So what is a sub n? It's 2n minus 3 over 3n plus 4. Is that less than, now a sub n plus 1 is 2 times n plus 1 minus 3 over, and now we have 3 times n plus 1 plus 4. So writing a sub n down, and then replacing a sub n, or n with n plus 1. Let me kind of clean up a little bit here. 2n minus 3 over 3n plus 4. Is that less than, let's see, 2n plus 2 minus 1, so 2n minus 3, which is minus 1. And then 3n, let's see, plus 3 plus 4 is plus 7. Okay, so is that true? Well, this one's not as obvious, all right? You might say, okay, look, the denominator here is bigger than the denominator here, right? This is bigger than this, so that means this should be smaller. But at the same time, these two are not the same, so this one's smaller than this one, so this should be bigger. So it's hard to just look and tell. So what I'm going to try and do is convince you by just algebraically working with this. So I'll multiply both sides by 3n plus 7. That'll clear out this. And then I'll multiply both sides by 3n plus 4. And that'll clear out this. And so what I'll get is this times this. So 3n plus 7 times 2n minus 3 is less than, over here, this times this. So 2n minus 1 times 3n plus 4. So I need to see if that's true. So let me go ahead and just multiply this all out. I get 6n squared. I get minus 9n. I get plus 14n.
and then I get minus 21. Is that less than 6n squared plus 8n minus 3n minus 4? I need this to be true in order to say that this is increasing. So right away I notice I have 6n squared on both sides, so I can subtract it on both sides, it's gone. Negative 9n and 14n, that's 5n minus 21. Is that less than, let's see, 8n minus 3n is 5n again, right? 5n again, and then minus 4. Notice I have 5n on both sides, so I subtract it, it's gone. Get negative 21 is less than negative 4. Is that true? Yes, that's true always. So since that's true always, this thing is always increasing. So we are good to go. It is an increasing function, or increasing sequence. Now I need to show it's bounded. So what do you think you can squeeze this between? What would you squeeze that between? Well, we can kind of cheat a little bit. We could have just figured in the very beginning, we could have said, you know, what, does this converge or diverge? And you could have done, okay, it's like L'Hopital, infinity over infinity, and you would have found out that it converges to 2/3. But sometimes it's not that easy, so we have to just look at the sequence and see if we can figure something out. Looks like the smallest number we ever get is negative 1/7. So I think it's safe to say that we think this is always greater than negative 1. And then we always think it's probably less than, let's see. These numbers don't ever appear to be bigger than 1, right? If we look at the rest of them we had, we always had the denominator was bigger than the numerator. So probably less than 1. If I can show this, right? I want to show that this is true, then I would show that it's a bounded sequence. So let me start with this left side. Is negative 1 less than 2n minus 3 over 3n plus 4? All right, well, I'll multiply both sides by 3n plus 4. And when I distribute through, I get negative 3n minus 4. Over here, all that's left is 2n minus 3. And let me get all my n's on one side. So I'll add 3n, I'll get 5n. And then I'll add 3 to both sides, and I'll get negative 1. And then negative 1 divided by 5 is less than n. Is n always bigger than negative 1/5? Yes, because it's a sequence. So this side checks out. Now let's check this side. Is 2n minus 3 over 3n plus 4 less than 1? Well, again, multiply both sides by 3n plus 4. You'll get 2n minus 3 is less than 1 times that is just this. Move all my n's over, so I'll have 1n on the right side when I subtract 2n. I'll subtract 4, I'll get minus 7. Is n always bigger than negative 7? Absolutely. So this checks. Therefore, it's a bounded sequence, it's monotonic, and therefore it converges. All right, let's look at the next one. N negative 1 to the n, or 39. N negative 1 to the n. All right, let's try and get an idea of what's happening here. If I write some things down here. If I plug in 1, I get negative 1. If I plug in 2, that's 2. Negative 1 squared is positive 1, so I get 2. And then if I plug in 3, I get 3, but then negative 1 cubed is negative 1, so negative 3. And then 4, and then negative 5, and then 6, and then negative 7. This continues. And if I look at this on a graph, a plot of the sequence, I've got at 1, I'm at negative 1. At 2, I'm at positive 2. At 3, I'm at negative 3. At 4, I'm at positive 4. And so what's happening is this is flipping back and forth between positives and negatives, but it's fanning out. It's getting bigger and bigger. So there's no way that this could be an increasing sequence. It doesn't keep going up. It doesn't keep going down. It's going back and forth.
And on top of that, it doesn't appear to be bounded, right? There's no number that I can pick that will be a ceiling or a floor for this that will always be between, that our sequence will always be between those. I can't say infinity. Infinity is not a number. It has to be a number that it's fixed between. So just by inspection, this is not monotonic, and this is not bounded. All right, number 40. N plus 1 over n. All right, so let's take a look at this. Let's try and get a feel for what's happening here. If I plug in 1, get 1 plus 1 over 1, that's going to be 2. If I plug in 2, I'm going to get 2 plus a half. If I plug in 3, I'm going to get 3 plus a third. 4 plus a fourth, and so on and so forth. This is really 2, and then if we get a common denominator here, we'll have 4 over 2 plus 1 over 2, it's 5 over 2. Here, if I get a common denominator, I get 9 over 3 plus 1, that's 10 over 3. Here, 4, we get a common denominator, 16 plus 1, 17 over 4, and so on and so forth. So what's happening if I actually plot this, if I plug in 1, I get 2. If I plug in 2, let's see, what's this? 2.5, bigger. 3, if I plug in 3, I get what? That's 3.3, something like that. So I'm going up. 4, I'm getting what? 4.25 or something like that. So it appears that the further I go out, the bigger it gets. Now I could confirm that by taking the limit as n goes to infinity. If I do that, that goes to infinity, that goes to 0, so this goes to infinity plus 0, which is infinity. So this thing is definitely not bounded. And as far as monotonic, well, is it always going up? It looks like it's always going up. Let's show it though. We have to actually show whether or not it's monotonic or not. So for monotonic, I want to show, I think it's increasing. A sub n is increasing just by looking up there. So I want to show that a sub n is less than a sub n plus 1. So let's try that inequality. I'm going to continue it over here. Okay, so I'm trying to show this. So I'm trying to show that n plus 1 over n is less than, when I plug in n plus 1, it's n plus 1 plus 1 over n plus 1. So that's what I'm trying to show. So let's see. Right now, I don't have to clear fractions right now, because what I can do is I can just subtract n on both sides. And then I can do, let's see, 1 over n less than 1 plus 1 over n plus 1. Why don't we move this to the other side? 1 over n minus 1 over n plus 1 less than 1. Is that true? Well, let's get a common denominator between these two. So you have to do an n plus 1 here, n plus 1 here. You have to do an n here and an n here. So what you'll get is n plus 1 times 1, which is n plus 1. Then you'll subtract n, and you'll put that all over the common denominator, which is n times n plus 1. Is that less than 1? So cancel those out, and what you get is 1 over n times n plus 1 is less than 1. I think we can convince ourselves that this is true right here, because the smallest n could ever be would be 1. And if I plug 1 in here, I'm going to get 1 times 2, that's 1/2. 1/2 is less than 1. And then as the bottom gets bigger, this gets smaller, so it's definitely going to be less than 1. But let me try and take it one more step. I'm going to multiply both sides by n times n plus 1. So it'll clear out on the left, it'll appear on the right. So I get 1 is less than n times n plus 1. And then I'll distribute through. And I think that's pretty obvious. Again, the smallest n could be would be 1. And in that case, I get 2 is bigger than 1. And then if you plug in 2, obviously that's bigger than 1. So I think at this point, I'm really convinced that that's true. So this is an increasing sequence, but it is not bounded, all right? It is not bounded. It might be worth it for me to show you how you could show it's not bounded. So what I'm going to do is I'm going to contradict myself here. I'm going to act like it's bounded, all right? Bounded above. So is a sub n bounded? Looking at that sequence, can I say it's bounded below? I can say it's bounded below because 0 is definitely less than 1 n. It's 1 over n. Because this right here is always a positive number, plus this is always a positive number. Definitely this is true, all right? You could go through and get a common denominator right here and put n squared plus 1 over n. You can multiply both sides by n and get 0 is less than n squared plus 1, and then you would say, yeah, that's obviously true. So it's definitely bounded below. Is it bounded above? Because you have to have both conditions for you to say it's bounded. So is it bounded above? Let me show how you would contradict yourself if you think it is. So suppose that you think that n plus 1 over n is less than some upper bound, all right? Then that would mean getting a common denominator here. N squared plus 1 over n is less than capital M, right? And in this case, n squared plus 1 is less than m times n. So check this out. If we pick n to be 1, then what happens? Remember, m is a fixed number, right? M is a fixed number. So if m is a fixed number, then let's let n be 1, and let's see if this is true. Well, 1 squared. 1 squared plus 1 is 2 is less than m than m. Well, okay, that's not bad. I mean, that's okay. That looks like if you choose your m to be big enough, then you can definitely make it bigger than the first guy, right? If I pick an m big enough. But let me show you how this would fail, all right? What if I choose my n to actually be equal to the capital M? Whatever you think the top bound is, I'm going to come in here and I'm going to use that as my n. Then this right here becomes m squared plus 1 is less than m times n, which is m squared. And then what happens is these two cancel. You get 1 is less than 0, and you've contradicted yourself. You've said, hey, look, I think that this is always less than some m. You can't change that. That's stuck now. And you say, all right, well, if that's true, then this has to be true. And then you come over and you say, oh, well, if n is 1, sure, it works. But if I go out far enough in my sequence, I will actually be able to come up with a contradiction of the inequality, which means that it must go the other way, and it must be bigger, so it's unbounded. That's just to show you how you could prove to yourself that it was not bounded above. All right, that's it for 8.1. Let's get into 8.2 now. You know what, I think I might just make this its own video. It's what, it's almost 30 minutes? Yeah, I'll make that its own video. Okay, in this video, what I'm going to do is I'm going to start doing, this is mostly a video for my internet class, I'm going to talk about the 8.1 sequences, but before I do that, I want to talk about a problem from 7.5 that involved finding the surface area when you rotate this function around the x-axis. But the big thing on this problem is that the interval that you're looking at is infinite. So I'm going to do an example here. We have a function e to the negative 4x on the interval x bigger than or equal to 0. So here's the graph of e to the negative 4x, and it goes out forever. We want to take that, we want to wrap it around the x-axis and find the surface area. When we wrap it around the x-axis, we get this thing that looks like a funnel, but it gets smaller and smaller and smaller, but it goes forever. It's kind of an interesting idea. It's very similar to a problem, a classic problem in mathematics called Gabriel's paradox. You can Google it if you want to look it up. It's a very similar looking graph. Has some interesting properties. But we're going to look at this one. And so what we need to find the surface area is the formula. Formula says that we're going to go 2 pi times the integral from a to b. So a to b is our interval of the function, which here is this, times this is the arc length piece, 1 plus the derivative of the function squared dx. So replacing everything, I'm going to go from 0 to infinity, because that's my interval. And because of that, this turns into an improper integral, which means we'll have to use the techniques from an earlier section in order to figure this out. We'll have to do a limit at the end, okay? Then we have f of x, 1 plus. Now the derivative of f, I did it over here. Here's the derivative of our original function. We're going to take that, we're going to square it. So I have to figure out an antiderivative of this. I noticed that the outside here looks like the derivative of this piece right here. So I do a quick u substitution. I let u be this piece in here. The derivative of that is this. I'm off by 16. You can see I don't have a 16 here, so I scale both sides by 16. And so I can replace e to the negative 4x dx, which is this piece and this piece. I replace that with 1/16 du, and that's right here, 1/16 du. And then the rest of it, 1 plus, this was u, so 1 plus u squared. Then I go to my book and I look at my formula sheets. Formula number 21 allows me to deal with this right here. So from here to here, I've taken the antiderivative using formula 21. And I've also put these two together to get pi over 8. And so I was kind of out of space, so I'm going to continue this problem now. I'm going to replace now all my u's in this answer with this. And then I'll take care of the 0 to infinity. So I'm at pi over 8. And then I have u, which is negative 4 e to the negative 4x over 2. Square root of 1 plus negative 4 e to the negative 4x, that quantity squared. And then plus 1/2 natural log of u, which was negative 4e to negative 4x, plus the square root of 1 plus negative 4e to the negative 4x squared, and that's that. And then I close my brackets. All right. Now, what I need to do is evaluate this. Remember, our original integral was 0 to infinity. So I'm kind of out of room, but over here on the side, I've got that bar that I put here. I go 0 to infinity. And that means when we plug in infinity, you can't really do that. What we do is we plug t in for all of these x's, and we let t go to infinity. So let me just look at this. There's one particular part in here that appears many times, right? Here it is, here it is, here it is, and here it is, right here. So what would happen if I take that, e to the negative 4x, I replace x with t, and then I let t go to infinity. Well, this is equal to 1 over e to the 4t. And if I let t get infinitely big here, this bottom gets big, the exponent gets big, e to infinity gets huge, this whole thing goes to 0. So anywhere, when I'm plugging in infinity, what's happening is everywhere I see an e to the negative 4x, it's really going to turn into a 0. So let's see how that changes things here. Okay, so plugging in infinity, this piece right here goes to 0, 0 over 2. That 0 should kill all this off. So this is all dead. And then if I plug in, go infinity here, that goes to 0. And then notice here, this is kind of interesting. This is addition, right? So we have to be careful. Over here it was multiplication. If this right here goes to 0, 0 times negative 4 is 0, 0 squared is 0, plus 1, this is just 1. Square root of 1, this was all 0. So this whole thing inside here becomes a 1. Natural log of 1 is 0. So it turns out that when we plug infinity in, or let t go to infinity, the whole thing goes away. It's just 0. So I have equals 0 minus, now I'm going to have my pi over 8. Now let's plug in 0 for x. So e to the negative 4 times 0 is e to the 0, which is 1. So that means all those blue pieces are going to turn into 1s. So let's see what we get. This is a 1 times negative 4 over 2, that's negative 2. Square root, 1 plus, that's a 1. 1 times negative 4 is negative 4 squared, 16, 16. Let me do that, 16 plus 1, root 17. And then we have, let's see, that's going to be a 1, negative 4, so plus 1/2 natural log, negative 4, and then this right here, go through it again, is plus root 17. Close it off. So now what I'll do is I'll distribute this through. So we get positive pi over 4 root 17. And then here to here we get negative pi over 16 natural log of negative 4 plus root 17. All right, I'm going to just double check that on my computer to make sure that that is the correct answer. Yep, okay. So that's correct. All right, so I hope, it turns out, by the way, to be about 3.649. 3.65. So if you had this infinite funnel and you were to look for the surface area, it would actually be finite, which is kind of interesting. Okay, let me now move on to chapter 8, section 1. I've got about 40 minutes here. Let me see how much I can get done. So I'm working again for my internet class just right out of the homework set. And I'm just going to pick some interesting ones here. How about 2? This will go quick. 2, they define a sub 1 to be 6. They define a sub n plus 1 to be 5a sub n minus 5. So this is what we call a recursive formula. They give you, for this sequence, they give you the first one, 6, the first number in the ordered list of numbers. And then every other number in this list can come from this formula. So if I want to know what a sub 2 is, then I'm imagining I'm using this formula right here, that the n plus 1 is 2. That means I'll have 5 a sub n, here this will be a sub 1. and then minus 5. So it's saying that the second number in the sequence is actually 5 times the first number minus 5. So this one is the nth number, and this is the n plus 1 number. So I know already what a sub 1 is. A sub 1 was defined to be 6. So 30 minus 5, 25. So the second number is 25. And then to get the third number, I'm going to do 5 times the second number minus 5. So again, to find the next number, I'm going to use the previous one. So a sub 3 should be 5 times 25 minus 5. So 25 was the previous number. 5 times 25 is 125, minus 5 is 120. So the next number should be 120. And then I continue this. If I wanted the fourth number, I'm going to do 5 times the third number minus 5. So it'd be 5 times 120 minus 5. And you can keep doing this. All right. I don't think these Formula 1s are really worth me going through because I'm going to do those in class in my lecture videos. So I want to see if you get those. Number 5, I'll just point out real quick, they defined your sequence to be 1 minus 0.5 to the n, and they want to know, does it converge or diverge? And so, hey, what's up? Yeah, it's okay.
Can I mix it up?
No? Do y'all need to come in here for something? Yeah, come on in.
Okay.
Come on in.
Well, I don't want to be on your film, okay?
You have to come through here.
You want a water? Please don't ask me.
Yeah. So what do you think of this?
You want a water? No. You want water?
No, thank you. I'm good.
We drink water here, but try. Okay.
All right, so on this one, all we're going to do is just realize that this right here looks like r to the n. And we know that if the absolute value of r is less than 1, then r to the n goes to 0. In other words, if you let n get bigger and bigger, this number gets smaller and smaller. So, I mean, it's pretty obvious. If you take 0.5 and you square it, it gets smaller. Cube it gets even smaller. Fourth degree gets even smaller. So what's happening is this whole thing right here, as n goes to infinity, that goes to 0. So that means that a sub n is headed towards something that's going to 1 minus 0, which means it's headed towards 1. So it actually converges to 1. All right, the next one, 6, I think that's also pretty self-explanatory. 7, let me look at 7. 7 gives you a sub n equals 4 to the n plus 1 over 9 to the n. So if we're trying to figure out if this converges or diverges, you let n go to infinity, the top gets huge, the bottom gets huge. And so you might be thinking like some sort of L'Hopital's rule or something, but I'm just going to do something a little easier. I'm going to split this into 2 fractions. And that really equals 4/9 to the n plus 1/9 to the n. This is kind of an interesting thing that we'll do a lot in this chapter. 4 to the n over 9 to the n, since they're both to the n, I can rewrite it as 4/9 to the n. Because if I want to go from here to here, I just do the n on each one, top and bottom. So I'm just going reverse. Here, same thing. We could have written that 1 as 1 to the n, because 1 to any power is still 1. So by using that fact, we can go back to this. And notice that this number is less than 1, and this number here is less than 1. And then using what I just did a second ago when we had this, we said that went to 0 as n gets big. Same thing here. This number in here is smaller than 1, so it's going to go to 0 as n gets big. This is going to go to 0 as n gets big. So the answer here is that this converges to 0. Okay, number 8 involves a square root. And the only thing I'm going to show you on 8 is just how to maybe start off. I give you square root n plus 2 over 36n plus 2. So we want to know what the limit is as n goes to infinity of a sub n, which is the limit as n goes to infinity of the square root of n plus 2 over 36n plus 2. Now, this is equal to this. So using the limit laws, you are allowed to move that limit inside the root. And that's all I want to show you. Because if you can move the limit inside the root, then all you have to do is the limit of this, and that's like number 6. So, all right, what else? Number 9. 9's interesting. 9 says you've got a sub n equals negative 1 to the n over 6 root n. And this one is an alternating sequence because of the negative 1 to the n. So like a sub 1 would be equal to negative 1 to the 1, which is negative 1, over square root of 1, which is 1, you get negative 1/6. But a sub 2 would be, let's see, positive, right? Negative 1 squared is positive 1 over 6 root 2, whatever that is. Then your next one would be a negative, and the next one would be positive, and so on and so forth. So we're trying to figure out if this goes and it converges to something. So what I'm going to do is look at a theorem that we did in class. The theorem says that if the absolute value of a sub n goes to 0, then a sub n goes to 0. So I'm going to take the absolute value of a sub n. The absolute value of a sub n is the absolute value of negative 1 to the n over 6 root n. And when we take the absolute value on top, it doesn't matter that it's negative 1. It could be negative 1 to any power. No matter what power I use here, I'm going to get either a 1 or a negative 1 up here. And when I take the absolute value of it, it's always going to be equal to. So I'm saying this is equal to 1 over the absolute value of this. Now again, if n is positive, which we're assuming it is, then square root of a positive number is positive. 6 times a positive number is still positive. So I really don't even need the absolute value anymore. Okay, the absolute value kills off the alternating part. So the question is, what's the limit as n goes to infinity of this? So the limit as n goes to infinity of the absolute value of a sub n equals the limit as n goes to infinity of 1 over 6 root n. And that's pretty obvious. As n gets big, this whole thing squashes down to 0. So it's 0. And because of the theorem, I can say, therefore, 3 dots means therefore a sub n must go to 0. Or in other words, negative 1 to the n over 6 root n goes to 0. That's using that theorem. So that theorem is really helpful because it allows us to get rid of that alternating part. All right, next one. A sub n is cosine n over 4. And so what happens as n goes to infinity? Well, what does cosine function do? That's basically a cosine function. Cosine goes like this, right? And since this is a sequence, we're only looking at certain points on that cosine. I don't know where they are. They're all over the place. And as n goes to infinity, those dots are not going to any particular place. You know, they're oscillating. They're hopping around all over the place. So you can't say it's going to 1. You can't say it's going to 0 or negative 1 because it keeps on jumping around. So this limit doesn't exist. We would say that that sequence diverges. All right, I like number 10, or sorry, number 11. So they give you an alternate notation for this. This still means we have a sequence. All right, so they could have written this and it would be exactly the same thing. All right, so what's happening as n gets big? This thing gets big, big number factorial is huge, big number factorial is huge, so we have like an infinity over infinity. We can't use L'Hopital's rule here. We can't switch this into a function of x and use L'Hopital's rule, so we have to do something else. And so what I'm going to do is use the properties of the factorials. So remember that I could rewrite this as 8n minus 1 factorial. And since the bottom factorial is bigger than this one, right? 8n plus 1 is bigger than 8n minus 1. I'm going to start peeling parts off this factorial. So the bottom factorial is 8n plus 1 times 8n plus 1, take 1 away. That's what the factorial does every step. And then the next one is 8n minus 1. And then the next one would be 8n minus 2, 8n minus 3, 8n minus 4, all the way down to 1. So this remaining piece all the way down, I could write as factorial. Notice that factorial is attached only to this one. So this factorial means the rest down. And notice that that is exactly that. So that's what I did. I noticed the bottom was bigger, so I peeled a few off. I cancel these out now. And so really this is just 1 over 8n plus 1 times 8n, and it's obvious from that that as n goes to infinity, the bottom blows up and this whole thing goes to 0. So the answer would be that it converges to 0. I'm just blowing through these quick because I'm just trying to help you out here. I think 12 is doable. 13 we can use the squeeze theorem on. I'm going to show you what tips you off to that. So on 13, a sub n is cosine squared n over 3 to the n. So as n gets bigger, we already said cosine oscillates and it doesn't go anywhere. So you might think, okay, this one doesn't exist, but the bottom is going to infinity. So maybe that somehow counteracts this one's crazy up and down behavior. Well, that's exactly what happens. So I'm going to point out to you, remember that cosine is a bounded function. Cosine is always between -1 and 1. The fact that you square it means that it's always between 0 and 1, right? You square anything, it can't be negative. So what I want to write down is this. Cosine squared n is less than or equal to 1 or greater than or equal to 0. You just have to agree with me on that and believe that that's true just by the definition of what cosine has to be between. And then what I'm going to do is I'm going to divide everything by 3 to the n. 3 to the n. 3 to the n. So this inequality holds true, right? If the original inequality was true, then if I divide everything by the same thing, it should hold true, as long as this is a positive number. 3 to the n is positive. So if it were a negative number down here, it would flip the inequalities over. But now let's let n go to infinity. If you let n go to infinity, well, 0 over anything is 0. N goes to infinity here. That's kind of what we're trying to figure out, like what happens here as n goes to infinity. Well, that has to be less than or equal to whatever happens to this when n goes to infinity. But that's obvious. 1 over a huge number is going to go to 0. So what we've done is we've squeezed the part that we're trying to figure out between two numbers. Those two numbers are going to the same place, 0. And so we squeeze our answer right in between 0 and 0. So the only place that this could possibly go is 0. Ooh, 14 is really nice. I think I'll help you get started, but I don't want to give it away. For 14, you're asked to find what this sequence is doing. N over 3 sine 3 over n. So as n goes to infinity, this gets huge, it becomes infinite, times, and then 3 over big number becomes small, it's 0, sine of 0, 0. So you get 0 times infinity. That's an indeterminate form. That's a bad situation. So here's my hint. This is a Cal 1 issue. First, we're going to look at this as a function of x. So we're going to switch this over to a function of x. That way we can bring L'Hopital's rule in. Remember, you can't work with L'Hopital's rule on a sequence, because for the L'Hopital's rule to work, you have to have a derivative. For the derivative, you're going to have continuity. We don't have that with this. I talk about it in class. So we still get infinity times 0 here, but watch. We're going to take this. We're going to rewrite x over 3 as 3 over x on the bottom, which is the same thing. If I flip that back up here, I get the same thing. But watch what happens now. As x goes to infinity, this goes to 0, sine of 0, 0. So the top's headed to 0. The bottom, 3 over infinity, is going to go to 0, so the bottom's headed to 0. Now you can use L'Hopital's rule. I won't do it. I'll let you do it. It is going to converge, though. Next one, a sub n, this is 15. A sub n is 1 plus 7 over n. How's my audio going here? It's good, okay. To the n. So what happens is n goes to infinity. This goes to 0. The inside's turning into a 1, but it's always just a little bit bigger than 1, so I'll put a little plus here. This is always a number that's just a little bit bigger than 1, but I'm raising it to a number that's becoming infinite. And again, in Cal 1, this is an indeterminate form. You have to figure out what happens here. The base wants to turn into 1, but raising something to a huge power should make it bigger, especially if this number is bigger than 1. It should try and rip it apart and make it huge. All right, so what we'll do is, again, we're going to have to bring in L'Hopital's rule. So I'm going to define this. I'm going to call it y equals a function of x, which was 1 plus 7 over x to the x. And then to use L'Hopital's rule on this, you actually have to take natural log of both sides. And you do that, you can pull the x out and then go to town with it. If you want, look in my YouTube playlist for my Cal 1 videos this semester on L'Hopital's rule, which is section 2. I don't remember if I put the title. In the videos on YouTube, I don't know if I put the title of those sections. I think it's 2.7. No. Where's... Oh, it's 3.7. So if you're having trouble with L'Hopital's rule, go watch my, my videos for Cal 1 on 3.7, L'Hopital's rule. The heck is that? That was interesting. I'm going to let you think about 16 and 17, because that's the whole point of those problems, just for you to try and figure out what's going on. 18 is really kind of weird. So let's take this one. 18. What is that? I downloaded this new app and it's making this weird noise now on my phone. I better see if I can turn that off. I think I want to uninstall that. Y'all just bear with me for a moment while I uninstall this app. Think about this though. What's happened as n goes to infinity? All right. I'll see if that helps. Hey, come on in, man. I'm almost done. Yeah, I've got about another 2 or 3 minutes, I think, on this. Maybe a little more, 5. So as n goes to infinity, this thing right here just keeps oscillating back. So like, if n is 1, I get -2. N is 2, I get 4, then -8, then 16, then -32. So the top is doing this. The bottom is getting huge, and it's becoming infinite. So you could say that the top is headed to infinity, the bottom is headed to infinity. The thing is that the top is switching back and forth between positive and negative big numbers. So this is really kind of like a what the heck is going on. So what I'll do is first let me see if that theorem that we had will work. That absolute value problem. If I take the absolute value, right? Take the absolute value of this, I need for it to go to 0 for this theorem to work. So let me see, the absolute value of the top is just going to be 2 to the n. So that's just going to, it's going to wipe out the alternating part, and then I'll have on the bottom 6n factorial. And then what I need to do is figure out what's happening here. Well, 2 to the n, let me just write down what 2 to the n would mean. It would be 2 times 2 times 2, and then I would have all the way, I would have actually n of those. And then on the bottom, I have a 6 out here, times n factorial would be n times n minus 1 times n minus 2, and then all the way down to 1. And so if I look at it this way, then how many of these things in parentheses will I have? So look at it this way. If I had, let's say, 5 factorial, I would have 5 times 5 minus 1 times 5 minus 2 times 5 minus 3 times 5 minus 4 would get me down to 1. So if I have 5 factorial, I have 1, 2, 3, 4, 5 of these, and that last one is 1. So notice that I would have n dot 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 all the way down to 1. So I would have a total of n of these factors. So these actually line up like this exactly. So we know the last one out here, the last one, no matter what n is, right? So like if I fix n, I know that the last one is 2. The one before it has to be 2, and this has to be 2, right? So we get 1. And then what happens to each of these other ones? Which is bigger here? This right here, 2 over n, is going to be, let me see if I can write this another way. I think it'll be easier if I swap it up. Let me rearrange things. Okay, I'm going to flip the whole thing over. So I'm going to put the 2 over 1 in the front, and then the 2 over 2, which is 1, times, and then at the back I've got 2 over n minus 2, and then 2 over n minus 1, 2 over n. So I'm looking at each of these here. Darn it, I went a little too far. Let me move my camera so I don't have to erase that, because this is the last problem I'm going to probably do. So these are a bunch of dots in here. Okay, so what I'm going to do is I'm going to show that this has to be stuck between two things. Oh, and I had the 1/6 out there. Okay, so what's happening here? All of this multiplied together has to be greater or equal to 0 for sure. And then over here, I want to try and get it smaller than something. And how about 1/3? How about 2 over n? So let's see if you agree with this. I'm not even going to mess with this right now, okay? But do you agree that that number has to be smaller than 1? Well, if n gets big, this number is going to be smaller than 1. This number is going to be smaller than 1. This next number is going to be smaller than 1. All the way until I get down here to this one, which is 1. And then I have over here these two together, which would be like 1/3. So all of these multiplied these here should be like 1/3, smaller than 1/3, and then this times 2 over n here. So all of this has to be smaller than, if all of that multiplied together is 1/3 times 2 over n, then that's definitely smaller than 2 over n. Hopefully you follow that logic. So for large n, as n gets bigger, these are all going to be true. These are all less than 1. And then now I use the squeeze theorem. I let n go to infinity, and this goes to 0, and then this side over here already is 0. So that means that middle sum must go to 0. So that means that the absolute value of the sequence goes to 0, which implies that the sequence itself goes to 0, and so it converged. All right. The monotonic part, increasing, decreasing, I will do examples of that in class, so you should be okay with those. I hope that that helps.